this wave function here is normalized. Surprise, surprise. Alright, so now we've got the wave function, and it's a superposition of two wave functions that correspond to two different discrete quantized energies, so E1 and E3. Okay, so let's now use the Schrödinger equation to find the expectation value for E. What's the average measured energy value? Like imagine you do the same experiment a zillion times. You set it all up in the same way every time, and now it's quantum mechanics, so you'll get differences in the answer each time, pretty much. So you have to use statistics. You have to find the average value of the energy. So this is what we're looking for. What's the average value of the energy E? Well, we did this a bit earlier. You could put, now E's just a scalar, right? It's not even a vector. It's just a scalar. It's just the quantity of energy. So we've done this a bit before, but you could have just an E here and psi star psi. Or now, since E is just a scalar, you can put it anywhere. You can put it here or here or here. Doesn't really matter. But if you put it here, then you've got like E psi, and that's the usual right-hand side of the Schrödinger equation, an eigen equation, in fact. And you'll have, so on the left-hand side, you'll have the left-hand side of the Schrödinger equation. So d squared by dx squared psi plus v psi, but v's nothing inside the well, right? Inside these limits. Well, I haven't written them here, but a and minus a. So the v's nothing, so that cancels out. So you're just left with the differential part of the left-hand side of your Schrödinger equation. All right. So this is what your expectation value for the E should be. It should be this. Okay. Well, then it just becomes calculus again. You take your psi. Now it's the general psi. It's not the time-independent wave function. It's not your U. It's your psi, the general form. In other words, here. Okay. So now you just plug that value for psi x of t. You just plug it in here, conjugate it, of course. Make the i's go to minus i's. And here again, well, you have to differentiate it, and then you multiply it by psi star, right? And after a bit of calculus, again, you get this, and again a homework question, and this time I bothered to mark it, but you should be in the habit now of, when you get this kind of mathematical derivation, if it's fairly straightforward, just fairly routine, then I ask you to do it. I can't put everything up here. It'd take me a zillion years to film it. Well, actually, to upload it. It's the uploading that's the drag, the bottleneck. It takes me for for about a dozen minutes of filming clip. To upload that to YouTube, it takes me several hours, literally. So I have to be conscious of time. So I shorten the story and expect the students taking this seriously and really studying it, who really want to learn, right? This is part of your course, course homework. All right. So the time dependence drops out. It just becomes a function of distance, position, but not time, and that just comes out of the mathematics. If you actually do it, you'll see why. You'll see all the time-dependent terms cancel, right? Okay. Well, when you do this, you get this answer. So you calculate these two integrals, you sum them, and you'll get this answer here, right? Now. that's calculating the expectation value for the energy, the average measured energy value, using Schrödinger's equation. And this whole thing, this whole session is really just a concrete example of where instead of having like general like sigma, Ci, psi I, the general superposed state, we now have a concrete case where we just have two wave functions that we superpose to get a more general, a superposed wave function, and then find what the values of your C1, in this case C1 and C3. We have two coefficients, and we will square them to get the probabilities of measuring energy E1 and E3, and the sum of those two squares, C1 plus C3, sorry, C1 squared plus C3 squared should be 1. So this session is just a concrete example of that more general idea of sigma, Ci, psi I, the general form of superposition. Right? Given the CIs, here's C1 and here's C3. We know the expectation value E using the Schrödinger equation approach. So what we'll do now, I won't be able to do it in this session, I've run out of board, but what we'll do next, immediately in the next session, is we will derive the same result for the expectation value of your energy by using these coefficients, these. Here's your C1 and here's your C3, your C1, your C3, and we will find the expectation value of your energy from these, and of course we should get this same answer, right? And what does that show? What does that imply? What's the logic behind that? Well, it shows, it confirms the idea that these coefficients, these here, are in a sense probability amplitudes. Right? Remember that word amplitude? It just means when you square it, you get something that makes sense physically, right? Something useful in physics. Well, in this case, when you square it, you get a probability of measuring a certain value for the observable you're talking about. In this case, it's energy. Right? The observable is energy. So this, when squared, will give us the probability of measuring the energy value as E1. And this, when squared, should give us the probability of measuring the energy value at E3, right? And so that C1 squared and the C3 squared allow us to calculate the average value of the energy, measured energy. So it should come out to being this, which is what we got using the Schrödinger equation. So it just reinforces the idea that the quantum mechanics is doing something right, something correct, and interpreting these C's here, these coefficients, as probability amplitudes, right? And we will keep doing this again and again. In fact, in several sessions, you can't see it yet, but the other end of the board, we will generalize this concept, not just to energies, but to any observable, any quantum mechanical observable, a measurable physical quantity. We will generalize this concept as a basic postulate, as one of the formal rules of quantum mechanics. So expect in a couple of sessions from now, I'll be really ramming this point home because it's basic to quantum mechanics.